Okay, 1.1 functions. So we're going to start with some definitions. A relation, and this is what we focus on in grade 9. Okay, a relation is an identified pattern between two variables. For example, a set of ordered pairs, x comma y. And we can represent relations in many different ways. We could represent them as ordered pairs. We can represent them as mapping diagrams. We learned that last year in grade 11, right? Like this. We can represent them as an equation, a table of values, or a graph. So maybe y equals something of x. Table of values are going to be x and y, and then whatever graph it is. Okay, so any table of values can be a relation, but not specifically a function. So a function is a specific type of relation, and every value of the independent variable, being x, corresponds to exactly one value of the dependent variable y. Okay, in other words, we say, and this is in quotes, for every value of x, there is only one y. We can tell whether or not it's a function by the vertical line test. So if any vertical line passes through more than one point on the graph, then it is not a function. Okay, and the domain, which we call D, of a relation is the set of all possible values for the independent variable, usually called x. And the range, which we call R, of a relation is the set of all possible values for the dependent variable, usually called y. So y values. So here's the function notation. In general, function notation, we write f and then in bracket the x. And this represents the dependent variable. We used to use y, like a y equals, and now we're going to use f at x equals. And what this means, so we read it f at x or f of x. I usually personally say at f at x. And what this means is some function, like the value of the function at some independent variable, which is x, right? So now we're substituting in f at x directly for y. Okay, so these are interchangeable. So it means that the value of the function, so the output for a given x value, input. Okay, given the functions f at x equals 2x minus 1 and g at x equals negative x squared plus 2x, we're going to find the following. So f at 2. If you remember, if we have f at x, what ends up happening is we're substituting this 2 exactly where the x is. So we know that f at x equals 2x minus 1. Therefore, if we're subbing in the 2 to where the x is, we can go ahead and sub in the 2 to this equation. So it's going to be 2 times 2 minus 1. It's going to be 4 minus 1, which is 3. Okay, now b, g at negative 1. So we know g at x has a different equation. G at x is negative x squared plus 2x. We can go ahead and if we're evaluating g at negative 1, we can go ahead and substitute in negative 1 to where the x is. Okay, we're going to bring this negative sign down. And then if we have negative 1 squared, we're going to have, well, negative 1 squared is just 1. And then 2 times negative 1 is 2. So we have negative 1 minus 2, which is negative 3. Switch the color. All right, g at x minus 1. So g at x equals negative x squared plus 2x. So this gets a little bit more complicated because now we're dealing with a binomial. Okay, so if we wanted to sub in x minus 1 everywhere where there's an x value, then we're going to go minus x minus 1 squared, and then plus 2. And then instead of writing x, we're going to, again, write the x minus 1. Okay, so this is going to be negative, and then x minus 1 squared, we're going to write it twice. And then this one we can go ahead and expand in. So plus 2x minus 2. Okay, so remember 2 at a time. I'm going to bring this negative sign down. And I'm going to go ahead and FOIL these two brackets. So x squared minus x plus 1. Okay, and then I'm just going to bring this down, plus 2x minus 2. Okay, and now I'm going to distribute this negative sign into the bracket. So we're going to negate all of these. Negate just means flip the sign. So x squared becomes negative x squared. Negative x becomes positive x. Negative x becomes positive x. 1 becomes negative 1. And then we have 2x minus 2. Okay, and now just collect like terms. Negative x squared. Those are going to give us 4x, right? X and 2x. And then negative 1 and negative 2 is negative 3. Okay, and then the last one. We have f at x minus 4 of g at x. So let's substitute. F at x is 2x minus 1. Now, if you don't know what this means, if you actually read this in order, it's telling you how to write it down. So I'm going to go negative 4, and then I'm going to write g at x inside this bracket. So negative x squared plus 2x. And then all we do is distribute this negative 4 into the bracket. So 2x minus 1 plus 4x squared minus 8x. Okay, and then just collect like terms. We get 4x squared, 2 minus 8 is negative 6x, and then bring down the negative 1. All right, recap of domain and range. So the domain of a relation is the set of all possible integers for the independent variable, which is x. And the range, likewise, is the set of all possible values. Did I say integers? I meant values. Okay, so for the dependent variable y. So if a function f is defined by an equation and no domain is specified, then the domain will be the largest set of real numbers for which the value of f at x is a real number. Exclude any real numbers from the function's domain that cause like division by 0, so you cannot divide by 0. Or that result is an even root of a negative number. So you can't divide by 0, we can't square root any negative number, okay? Because those aren't real in like the real number system. And this is how we communicate what the domain and range are. So first of all, we use these squiggly brackets like this. And what this is a set or like a collection of numbers, elements or members. Okay, this is actually like an E. I think it's epsilon in Greek. Okay, so we would say like X is an element or Y is an element. And that's how we would write it. So E stands for is an element of. Then, I mean, if you're reading a textbook, these are bolded letters, but when you are, when you're writing it out, usually I just put like 2 lines. Okay, so bolded letters indicate a number system. Systems that you've encountered are, usually we put like the real number system. So I do the double stick for the R. You can also do integers, which is Q. I'd also accept an I, but it is, or I said Q, Z. Rational numbers, Q, natural numbers, N, there's whole numbers, W, okay? But these are like the major ones. Usually we quote it in R or integers in Z. Okay, so XER such that, or YER such that. Okay, and the such that is a line. It can either be vertical or forward. I usually put a little bit forward. Okay, and then you write the conditions of the domain and the range. So an example of this is the domain is the set of elements of X such that X is an element of the real number system and X is less than or equal to 5. And then when you put the squiggly bracket on the other side, that ends that set. Okay, the domain is equal to the set of all X such that X is a real number and X is greater than or equal to 5. That's how you would read it. Okay, so let's go ahead and do example 2. So we're going to find the domain and range for the following relations below, and then we're going to identify whether or not it's a function. So when we have integer values, we can just list them, which may get a little tedious, but that's okay. It's usually not too many. So let's write X is an element of the real number system such that X equals, and then we're going to look 8, -2. So we're going to put these in order. -2, 1, 2, 8, and 8. So 8 and 8 you don't have to list twice. It's a repeat, you just list it once. Okay, for the range, Y is an element in the real number system such that Y equals, and then we go in order. -3, 4, 6, 7, 8. -3, 4, 6, 7, 8. That's it. Okay, and now as a recap of what a function is, each X has only one Y. That's what a function is. So what we have to do is we have to take a look at all of these X values and we have to say, do any of these X values repeat? So 8, -2, 1, 8, 2. Yes. This value repeats and this value repeats. So if these were graphed on a graph, and this is 8 and this is -3, and this is 8 and this is 6, 2 points would be here, and it would fail the vertical line test. So this is not a function. So you have to be able to tell just by having a duplicate X, right? Because then you can just tell like by the numbers or maybe graph it, but this is very tedious to graph. Okay, B is also discrete. So we're going to write domain and range. So this entire circle is the domain. These are the X values. And this entire circle are the Y values. So X is an element of the real number system such that X is equal to, so we can write this one of two ways. We can either write it as 0, 1, 2, 3. Okay, the other way that we can write it is we can write it as part of the integer values. So since there are no breaks in the integers, 0, 1, 2, 3, since it's hitting every single integer, we could put like X as an element of like Z, which is integers, such that, and we can put X is between 0 and 3. Because this is not the real number system, we're implying that between 0 and 3, including 0 and 3, we're just going to hit every single integer. Okay, and then the range. Y is an element of the real number system such that Y equals 2 and 4. Okay, you can write real number system because it's very general, and then you're going to narrow it down to 2 and 4. All right, for these ones, for C. So C is continuous. It looks like an exponential function, and it looks as though we have a horizontal asymptote at -2. Okay, so for the domain, we're looking at, does it hit here? Does it hit here? And we're looking at every single value of x that this is going to hit, right? So XER such that, so x is between, so if you want to say x is between, and this, you can make this note on your side, okay? We can use, I call them crocodiles. We can use crocodiles like this. This is going to be smaller, the smaller number, and then the bigger number. So actually for this one, it's just XER. X is going to hit every single number left and right. So we can actually close that bracket. Make this note though, and we're going to come back to it, okay? And for the range, okay, start with the YER, especially because it's continuous, right? So it's going to hit every single number, every single real value, such that for this scenario, y is greater than -2. So because -2, I'm assuming that this is a horizontal asymptote, it's never actually going to touch the -2. So it's going to get infinitely closer to it, but never touch it. So y is greater than -2. And if you forget where the crocodiles have to go, the crocodile has teeth right here, right? So nice big teeth, and it's eating like the greater one. It's eating more food. So y is greater than -2. Okay, D is discrete again. Likely you're not going to see many discrete examples. It's more going to be continuous for the rest of the course, but these do exist. So I set up the domain and the range the same. XER such that, YER such that. Okay, so for the x is going to equal 1, -2, and -3. I should put these in order. So I should put them -3, -2, and 1, right? Lowest to smallest, or smallest to largest. And for y, we have -3, -2, -1, 0, and 1. So -3, -2, -1, 0, 1. Okay, so we have for E, x squared minus y squared equals 9. All right, I don't know what this looks like, so I go to Desmos and I say, okay, Desmos, what does this look like? So now we have a graph, and the assumption is that this graph extends those ways forever and ever. So for the domain of this graph, let's set it up as XER such that. So if we're at -infinity, it's going to hit every single number until it gets to 1, 2, 3, 4. This is -3. So we can say x is less than or equal to -3, right? Because -3 to -infinity, we're going less than, and it's going to hit every single number less than. Okay, then now you can put a comma because it's kind of like making a list. So now x is also going to be greater than or equal to 3. And where we see this is that we start again at 3. So there's like a huge gap where this graph is not defined. And then we start again at 3 and we go all the way up to infinity. Okay, set up your YER. So we can see that y, so this is the y-axis. We're looking at all of these numbers. Y goes up and down forever, so we can just put YER, done. All right, F. So let's set up domain and range. And this is a nice parabola, grade 10. Bringing it back. Okay, so domain. Going left and right, I'm going to tell you this is going to go left and right. Even though it's going down faster than out, it will still go out forever. So the domain is XCR. It's going to hit every single number. Also, when you actually look at a quadratic, you can technically sub in any number to X. So by being able to sub in any number to X, it is XCR. Okay, and now range. So this graph, quote unquote, starts at 2 and it goes down. These numbers get smaller and smaller until they reach negative infinity. So we can say that y is less than or equal to 2. Okay, it's less than because this nice crocodile is going to eat the 2, y is less than. Okay, and just a recap of like quadratics here, we have y equals 5x minus 1 squared plus 4. So our vertex is 1, 4, right? Remember, there's that built-in negative sign there, so we always flip the sign for the x value of the vertex. So if we were to graph this on the side very quickly, we would get the vertex of 1, 4, and then this, because the leading coefficient, the a value is positive, it's going to open up. So for every single quadratic, the domain is XCR. Done. Okay. And then what we want to do for the range is we want to locate the y value of the vertex, just like what we did in the last one. It's 4. So is y greater than 4 or less than 4? Well, it's going to be greater than. So y is greater than or equal to 4 because it's going up. Okay, I want to talk about open intervals, closed intervals, and then half open, half closed. Okay. So when we see an open interval, the endpoints are not included. Okay, so in the domain and range that we were just doing with, I call the crocodiles, they're called inequality symbols. So with the inequalities, it would be open, it would not have the underline, right? So for the actual interval portion, it's going to have round brackets. Okay, and when we show this on a number line, these 2 points are open circle. Okay, so this column is set notation. This column is interval notation. And if you guys are better at doing interval notation, I personally like interval notation better. Set notation with the crocodiles, I find it a little bit more confusing. Okay, but that is what you're going to see in university. Actually, you're going to see both. So we'll teach both. Okay, closed interval, all the endpoints are included. So this would have an underline. This inequality would also have an underline. How you see this in an interval notation is big box brackets. So instead of round brackets, they're box brackets. And how you'd see this on a number line is these points filled in. Okay, and then half open, half closed. So you can have a combination. So this is just one example, but you can have this vice versa as well. So x is greater than or equal to -2. So because this one is underlined, this -2 is closed. These correspond. And this bracket on the -2 is also boxy. Okay, and then on this side, x is less than 4. So because there's no underline here, we use the round bracket and we use the open point. Okay, interval notation is another way of writing continuous sets of real numbers. Intervals use brackets, so they look somewhat like an ordered pair. So you have to really, really think about what the question's asking you. Don't just think like, oh, let's plot this. Okay, think am I talking about an ordered pair or am I actually talking about an interval? Okay, they do not denote a specific point. Again, it's a shorthand way of denoting the beginning and the end of an interval. Okay, I'm going to do this example, and sometimes we're going to use a union operator, which is like a U like this, okay, instead of a comma. So we have -4 to -2, and those are both closed. So we can go -4, comma, -2, both closed brackets. Or, okay, we have -1 to 1, both open. So open bracket, -1 to 1. Or we have we have 1 to 2. 1 is open, 2 is closed. And then we just have 1 point, so 4. Or let's just put 4 in a box because it includes 4. Okay, write the domain and range for each of the following relations using set notation and interval notation. Okay, so set notation is domain and range. Again, A is a parabola. Parabola is our XER. Range is going to be YER such that we're going to locate on the y-axis the bottom or the topmost number. So this time it's 0, and we're going up. So y is greater than or equal to 0. Okay, or the interval for x, oh, I don't know why I'm going to use that. For the domain, we're going from -infinity to infinity, right? So -infinity would occur over here. We're going to hit every single number, and then infinity. Okay, for range, we're going to start, quote unquote, start at 0 and go up. So we're going to go from 0, we're including 0 though, all the way to infinity. So please make note, infinity is always open brackets because we can never truly reach infinity, because as soon as we reach it, it just keeps going. It's always out of touch. Okay, next one, set notation. So domain, range. So this one is, it looks like a parabola. So we're gonna go from -infinity all the way to 1. So here's the thing, we do include 1, but then when we jump up here, we don't include it. But then we do include 2, and when we go down here, we don't include it. But it does, like the graph does hit 1, it does hit 2, and then we go to the right forever. So essentially, domain is XER. Okay, and domain is -infinity to infinity on interval notation. Okay, now YER goes, we're going to hit 0. Oh, and because this is going to hit every single number, we don't even have to look at this side of the graph because we know that it already satisfies every single y value. So y is greater than or equal to 0. In other words, we're going from 0 to infinity.